All right, here we are. So today we've got a couple of things to do. For one thing, we need to go over the Chapter 11 problem sets, of which there are two. And by the time we're done with those, you'll be experts in probability theory. So let's go get those open. And then if there's any time left, we'll go back to Chapter 12 and pick it up where we left off. So let's get those going. All right, so we'll start with the first one, of course. Now, let's begin at the beginning. Now, suppose that an experiment consists of flipping a coin twice. The event A represents at least one head turns up, and the event B is defined as both flips or tails. Now, I've added this little comment here. Since each flip is equally likely to be heads or tails, each element in the sample space is also equally likely to occur. So we'll need that information as we go along. Now, the first thing we always want to do in these cases is identify the sample space. If you don't get this part right, all the questions will be wrong. So we have to be very careful here. Luckily, this is a very simple case, and you can probably imagine what it looks like. But what I've done here is I've drawn this little tree here, a binary tree it's called. And so the idea is that at each of these points, we flip the coin, and one of two things can happen. Initially, we flip the coin the first time, and we get either a head or a tail. And then once we've got our head, that means the next flip can either be another head or a tail. And then on the right-hand side, if we flip the tail first, the next coin can either be a head or a tail. So altogether, there's four possibilities: HH, HT, TH, and TT. So we gather them all up into a special set, which is called a sample space. All right, and so there's four of them, all of which are equally likely to occur. And so we use that as a starting point for all of our calculations. And then we're going to ask ourselves what, by the way, I forgot to mention this, I think. Sample points are simply elements of a set when we're dealing with probabilities like this. In other words, the sample space, each element is defined as a sample point. So therefore, we want to know which points belong in A. Well, how do we know? Because we define A to represent at least one head turns up. So basically, if you look at the entire sample space, you'll look and see that in the first three cases, we've got at least one head. It's only the last case with two tails that there are no heads. So the set A contains the elements HH, HT, and TH. And also, we call this an event. It formally is known as an event because it is a subset of the entire sample space. Okay, so this is what we mean by an event. It is itself a set, which is completely contained within the sample space. Now for B, B was defined as both flips or tails. So therefore, now clearly that would be this case, TT. That's the only time when we get two tails. So we've got our sample space defined. We've got our two sets defined, or two events. Now all the rest of these can be done, all these probabilities, basically by applying the rules that we learned. And in many of these cases, there's at least two different ways of getting at the same answer. So I'd like to go through all of them in each case, and you can decide which one you like the best. Okay, so in other words, you always can decide which approach you want to do and go with that. So for example, what would be the probability of A? All right, well, the way to think about this is that it contains the elements HH, HT, and TH. So always this option is on the table. What we can do is calculate the probability of each of these elements individually and then add them up. Now, if you notice, each one is listed as 0.25. Now, why is this happening? Just as a reminder, each element of the sample space is equally likely to occur and there are four elements whose total probability is 1. Okay, therefore, each element has a probability of 1/4 or 0.25. Oh, don't worry about it. You're fine. It's fine. Okay. So yeah, I just want to mention that right up front. Each of these individual elements has a probability of 0.25. So each of these has a probability of 0.25. So here I can literally just add them up and come up with a total of 0.75 or 75%. Now, the other option we have, you may remember from the slides, when we have a sample space where all the elements are equally likely, there's a shortcut we can use where all we have to do is basically count up how many elements are in A and how many elements are in the entire sample space. So this symbol means number of elements in set A, and this symbol is the number of elements in set of the entire sample space. Now, of course, in this day and age, people are using this thing for other purposes like hashtags, but they have traditionally been used to represent the number of something, like here, the number of elements. So we'll continue to use that notation here. And so because the sample elements are all equally likely, we have a shortcut available to us, which basically says, take the number of elements in A, divide by the number of elements in the sample space, and you're good. And you can see that it did, in fact, work out correctly. Now, if you had a sample space where all the elements were not equally likely to occur, you can't use this approach, but you can always use this approach. Okay, like imagine for some reason the coin is not equally balanced. And so heads, let's say, have a probability of 0.6 and tails have a probability of 0.4. Then each of these will have a different probability. And you'd have to use this approach to come up with this probability. But that's not the case here. So either one of these will be fine. All right, good. So you can see, yes, like I said, there can be multiple ways of getting at the same results. And you can decide which one makes the most sense to you and go ahead and use it. All right. Now, based on the same logic, therefore, B must have a probability of 0.25 because it consists of a single element, TT. And remember, each of these elements has the same probability, which is 0.25. Or alternatively, you can just recognize that there's only one element in B out of 4 in the entire sample space, and that gives you 0.25. So now in part F, we're looking for the probability of A intersect B. So what I would like you to notice here is that if you look at these two sets, they have no elements in common, do they? No, they do not. What does that mean? Well, their intersection then is the empty set. Now, I mean, a similar situation would arise if, let's say that A represented the red cards in the deck and B is the black cards in the deck. Clearly, there are no elements in common because there's no cards that are both red and black. So those two sets would also have, their intersection would be the empty set. So when this happens, the probability of that intersection is defined to be equal to 0. Okay, so in other words, since there's no elements in the set, that probability is equal to 0. All right, so always remember that when there's no elements in common, the probability of both of these events being true has to be 0. This is one of the axioms of probability, by the way. And also, I'll just add as a note on the side here, this is known, and you don't have to worry about this, but this is known as an impossible event. Okay, it can't happen. Therefore, the intersection is empty. The probability of this intersection is 0. All right. So yeah, we're not terribly excited about vocabulary in this class, but certain key terms you should be aware of. Now, how about this one? This is the other extreme. This is a union. That union means we're adding together all the elements in both sets. So it can't be, well, it can't be empty unless A and B are each individually empty. Instead, what happens is we just combine them into one big new set, and I've repeated them here so you can see them again. And just look what happens here. When I add them together, I have all the elements in my sample space. Look at this. The union of these two sets is the entire sample space. So that's an important result too, because that implies that the probability of this union is therefore equal to the probability of the sample space, which we know from the axioms of probability is equal to 1. Okay, so that is one way you could explain why this probability is 1. Another possibility is to actually do the individual probabilities like we've done before, and we added them up this time, and we ended up with 1. It has to be the same. So what other option is there? Oh, what about this one where we count them? So there's 4 elements in this union out of a total of 4 for the entire sample space. So we end up with 4 out of 4, which is 1. So we've got 3 options in this case for calculating that probability. Just remember, this is the one that always works. The others depend on our particular case. Very good. Now for the next one, you can see coming up next, probability of A complement. All you have to do is use that very easy complement rule that we studied. So whatever A is, 1 minus that probability equals the probability of A complement. And so here that would be 1 minus 0.75, which is 0.25. Yes, we like the complement rule because it's easy. All right, excellent. Now this is followed by the probability of B complement, and so naturally enough, you'll use the same rule. We'll just go ahead and calculate the probability of 1 minus the probability of B, which is 1 minus 0.25 or 0.75. All right, now we save kind of the hardest ones for last. The conditional probabilities. So for these, you want to make sure you remember how they're defined. Let me show you what that's all about. Here we go. So remember, when you've got a conditional probability, in the numerator, you have the intersection of these two elements or events. In the denominator, you have the probability of the second value right here, this B. This has to go in the denominator. Now, here the case is very simple because if you recall, the intersection between these two is empty. That probability is 0, so no matter what's in the denominator, this ratio will always be 0. So logically, I mean, remember, B means 2 tails turned up. A means that you got at least 1 head. So if you know that 2 tails turned up, it's not possible for A to be true as well. This is a logical impossibility, and so therefore we end up with 0. Okay, now we also want to try the other conditional probability that we know and love, B given A. Now here, if you notice, the formula is similar but not identical. We have the intersection in the numerator. In the denominator, we have the probability of A. Okay, but now once again, because A and B are mutually exclusive, in the numerator we have 0, The denominator is 0.75 in this case, but it doesn't really matter because that ratio will always just be 0. All right, now, here's some conceptual questions for us. L, all right, so are A and B mutually exclusive events? Now here, there's a few different ways of explaining why the answer is yes. Oh, only 2. No, there's 3. Okay, good. Number 1, you could simply point out that the intersection of A and B is the empty set. That's enough to prove that they're mutually exclusive. Or you could point out that the probability of their intersection is 0. Again, that's all you need. But if you want to use English to explain yourself, you could use the English statement that A and B have no elements in common. That is, again, enough to prove that A and B are mutually exclusive. We have nothing in common. All right. And like, for example, let's say you had the even numbers and the odd numbers. They have nothing in common, and they must be mutually exclusive. All right. What about the next one, though? The next one's a little bit more challenging. We're going to find out if the events A and B are independent of each other. Now, independence requires 2 things to be true. We have to test them and see if they work out or not. If one of them fails, we can stop right there because that means we're done. Oh, what happened here? They got squished. Oh my God. All right, let me fix this. I think the problem is when I write on here with the marker, if I start changing the pagination, it can affect the rest of these. No, oh, this is so annoying. That's all right. I'll get it straightened out. Okay, I wanted to remind everybody that the 2 things that must be true for independent events are that the probability of A given B equals the probability of A, and the probability of B given A equals the probability of B. So what we have to ask ourselves is the following question. Is that first condition true for our particular case? All right, so let me just, yeah, see the spacing is a little bit off now, but that's okay. All right, so is it true? Now, remember, we just got through calculating a few minutes ago the conditional probability of A given B. Remember, it was 0. And the probability of A we calculated a while ago, and it was 0.75. So these are not equal to each other. And that means we can stop our testing. We don't need to bother checking the second condition because we've already proven that A and B are not independent of each other. Okay, if the first one had been true, we would have checked the second one. And if it was also true, we would have concluded that A and B are independent. But because the first one is already false, we're done. A and B are not independent. All right, now the next question is one of our favorites, the joint probability table. It's one of our favorites because it's so easy. So what I've done is I put together a table. It's meant to represent the probabilities of choosing different flavors at Starbucks. Okay, so in other words, what they're telling us is that out of the coffees that they're producing, these numbers tell us how they're distributed. For example, 12% are decaffeinated Sumatra, 24% of regular Sumatra. And we can do the same thing for the Komodo dragon and Antigua. And these, of course, are simply the sums. So they've broken it up by whether it's decaf or regular, and then by the flavor, Sumatra, Komodo dragon, or Antigua. I bet you didn't know they make Komodo dragon, did you? Yes, they do. They have a flavor called Komodo dragon, and there really does exist. I think we've already figured this out at somewhere. I seem to remember looking this up on the internet, but the Komodo really are Komodo dragons in Southeast Asia. They're pretty nasty looking creatures too. But with this table in front of us, and if you notice, we don't have the raw totals like we did with the business students. All the numbers have already been converted into probabilities. So as a quick example, if I want to know the probability that a randomly chosen coffee is both Sumatra and decaf, look how easy this is. I just go right to the table and look for the intersection of decaf and Sumatra, and look what I found. That's my probability, 12%, or 0.12. And it's that easy. All right, so now I'm going to split the screen here so that I can see everything without scrolling up and down. All right. So let's look at the rest of these. How about R and A, regular Antigua? That's right here, because it's at the intersection of regular and Antigua, which is an island in the Caribbean somewhere. I think it used to be a Dutch territory, but it's down there somewhere if you look at a map. This is one of Starbucks' favorite flavors. And of course, Sumatra is actually in Indonesia. Okay, if you were wondering, that's an island in Southeast Asia, but I mean, specifically it's in Indonesia. All right. And of course, the reason why some of these names just tell us where the flavor comes from directly. Like obviously Sumatra is grown in Sumatra, one of the top coffee growing regions in the world. Anyway, R and K means regular Komodo dragon, which of course is right here. See how easy this is? Now, for the rest of these, it's not quite as easy, but all the information we need is obviously on this table. Like S, just plain S, what does that mean? That means Sumatra, whether it's decaf or regular, that number is 0.36, okay? Because of all the Sumatras add up to 36% of the total. And then I can do the same thing for regular. I just add up all the regulars across this row, and my total is 0.58. Aha, now all of a sudden I've run into a rule. What rule am I looking at? The probability, this is my complement rule. The probability DC, D complement, equals 1 minus the probability of D. And so D, we have to look it up in the table. And that turns out to be 42%, or 0.42. So therefore, the probability of D complement is 1 minus that, which means 0.58. All right, now we've got some more interesting ones coming up down here. Now, I do want to mention here in the slides, in case I didn't mention it, I mean in the notes here, in case I didn't mention it, with these tables, the columns are mutually exclusive of each other. There cannot be any overlapping between the columns. And the same thing is true of the rows. There cannot be a flavor that's both decaf and regular, for example, or a flavor that's both Sumatra and Komodo dragon. So these are all independent events. Not independent, mutually exclusive. That's important because now when it comes time to apply the addition rule, which we do here, we can use the simplified addition rule. Okay, so there's no need to subtract the intersection between them because it doesn't exist. So instead, whenever we have a union in this table like this, we can just add those together. So the probability of getting either Sumatra or Komodo dragon is just the sum of Sumatra 0.36, and Komodo dragon 0.20. So the grand total is 0.56. So in other words, if I randomly pick one of these bags off the shelf, the chances of it being either Sumatra or Komodo dragon is 56%. The rest of them are Antigua.
I have a question
Yes,
about F. What is the sorry, I was zoning out a bit. What is the purpose of subtracting 1?
well, that's because if you recall from the way complements are defined, probability D plus probability D complement equals 1. And that's, again, just because of the way complements are defined. And so
Okay, I
therefore,
see.
this is just an algebraic rearrangement of this equation.
Gotcha. Okay.
All right. Anyway, so we've got a couple more of these. Here we go. How about K union A? That means either Komodo dragon or Antigua. So just like before, we can literally just add up those two. K is here, A is here. You add them up, and there you go. 0.64. Again, we're using the simplified addition rule because the columns are all mutually exclusive of each other. And it's that easy. Man, all of this stuff seems pretty easy, doesn't it? This might prove to be the easiest test of them all. You never know. All right, now, D given S. Now, this is a conditional probability, so remember, you've got to know how that definition works. This one means we've got the intersection of D and S in the numerator, and S goes in the denominator, because that's this probability right here always goes in the denominator. These you can look up in the table, although I think we've already seen all of these before. D and S is that 0.12 up here, and S is simply the total of Sumatra. So that works out to 0.12 over 0.36. This is equal to 1/3, but you can write it as 0.33. So basically what it means is that if you pick a Sumatra, a bag of Sumatra, what is the likelihood that it is decaf? So in other words, you already know that it's Sumatra. Now we want to know the probability that it is decaf. Then we have, with the exact same setup, R given A. In other words, if we pick a bag of Antigua, what's the probability that it's regular? So therefore, we need the intersection between R and A in the numerator. A goes in the denominator because that's this probability right here. And so we look up these numbers. R and A, regular Antigua, has a probability of 0.22, and A by itself has a probability of 0.44. So in other words, you can see for yourself within the Antigua column, half are regular and half are decaf. So the answer is 0.5. All right. I think there's one more. Yes, K given R. Komodo dragon given regular. So among all the regular flavors, if I choose a regular flavor, what's the likelihood that it's Komodo dragon? So I need to know the intersection between K and R right here. 12% divided by 58% total regular coffee. And so that works out to approximately 0.21. Well, that wasn't so bad, was it? No. All right, now. That was all of it. Okay, good. We're all set. Now there's a second one. And by the time, like I said, we're done with the second one, you'll be experts in probability theory, which is good because the final exam is 100% based on chapters 11 and 12. It's not comprehensive. All right, I think that should be cause for celebration, don't you? I would be celebrating. Well, if I were 19 years old, yes. Okay, now I just want to learn more math all the time, but you know, of course, here you want to get the best grade. But yes, it's just the last two. Anyway, so there's some similar type problems here, but there's some different ones at the end as well. So why don't we start at the beginning? So this time our experiment means we're picking a card from a deck, but we're replacing it and then picking another one. And because of that, the probability of the second card being either red or black is not affected by what happens to the first card. You might recall we called this sampling. In fact, I think this, I can sneak this in here. This is known as sampling with replacement. We're taking a sample, which is the card, we're looking at it, we're putting it back, and then we're picking another one. Now, A will now be the event that both cards are red, and B will be the event that at least one card is black. Excellent. Now, what is the sample space of this experiment? Now, by the way, if you notice, because we chose with replacement, that indicates that choosing a red or a black on either this first or second draw is equally likely to occur. So just like with the coin flipping experiment, in our sample space here, all the different possible elements or outcomes will all have the same probability. And since there's only 4 possible outcomes, just like in the previous problem set, each of these elements will have a probability of occurring of 0.25 or 1 out of 4. And you can draw the little tree if you want. And you'll see that the outcomes are RR, RB, BR, and BB, where clearly R means red and B means black. So what sample points belong in the sample space? Oh, I forgot to write it down here, didn't I? S equals RR, RB, BR, BB. That's our sample space. And again, this is simply a set that contains all the different possible outcomes of an experiment. It's not always the case that each outcome is equally likely, though. In fact, usually it is not the case. But here we're keeping it simple and we're assuming that they're all equally likely to occur. And so now what sample points or elements are contained in A? Now remember, A means both cards are red. So that's pretty simple. A simply contains this element RR. Now for B though, remember B means at least one of the cards is black. Let's see, where is it? Yes, no, it's up here somewhere. There it is. B is event, defined as the event that at least one card is black, which means this is out, but these other 3 all belong to set B because they all have at least one black. So we can write this out as RB, BR, and BB. All right, now of course we're going to basically go through and calculate all the same probabilities we had in the last problem set, starting with the probability of A. And you'll recall that because each of these is equally likely to occur, the probability of 2 reds is 0.25. So the probability of A is the same thing as saying what's the probability of getting 2 reds, which in turn is 0.25. Okay. How about E? What's E? Oh, before we continue, remember there's at least 2 different ways of doing this. So for example, what if we do it this way? What if we count the number of elements in A and divide by the number of elements in S? We can do that too, because we know that all the elements are equally likely to occur. And that of course gives us 1 out of 4 or 0.25. They can't be different. All right, beautiful. Now E, in part E, we'll compute the probability of B. And if you recall, B contains the elements Let's see. Let me go sneak that back in here. Here we go. Just as a quick reminder, B is these three elements. And so therefore we can calculate the probability just from the individual probabilities. 0.25 plus 0.25 plus 0.25 equals 0.75. And again, we have the option of just saying, well, you know, there's three elements here out of four in the entire sample space, all of it which are equally likely. So therefore, I can think of that as 3/4 or 0.75. Okay, so either way, you'll get the same thing. Now, how about the intersection? Those are the two sets. Do they intersect at all? No. Once again, just like in the previous problem set, they do not have any elements in common. Now, I don't want you to think that it's always this way. In fact, this is often not the case, but here we just happen to have two examples where the two events do not have anything in common. We'll come up, don't worry, we'll have more examples where they do have plenty of things in common, but here they do not. And we point out here that A and B are mutually exclusive, meaning they have no elements in common. And actually, let me make a note here. So because they have no elements in common, that guarantees that the probability of that intersection is 0. The other option you have is to simply write out the elements that belong to that intersection, but you'll see very quickly that that's the empty set. So don't forget, when you just have these two braces here, that's what we mean by the empty set. It's a set that contains no elements. Like the set of all people who like beets. All right, well, maybe not. I shouldn't say that, but it's probably going to be a small set any way you look at it. But the empty set means there's no elements. And therefore, by definition, remember the probability of the empty set is 0. So the probability of the empty set is 0 based on the axioms of probability. And we also say that in terms of terminology, then in that case, this intersection is said to be an impossible event. But then with the union, we're bringing the sets together, remember? So we've got these two sets, and when I bring them together, look what happens. Oh, they give me the entire sample space. So what I can do is say, all right, well, I can calculate the sum of the individual probabilities. 0.25 plus 0.25 plus 0.25 plus 0.25 equals 1. Or I can add up how many elements are in this union, which is 4, and divide by the size of the sample space, which is also 4. And of course, that means that I'll end up with a 1. And as if that weren't enough, there's another option here. We just note that A union B is the entire sample space, which guarantees by the axioms of probability that its probability is 1. And we sometimes call this a certain event. It's guaranteed. The union is somewhere in there. One of those elements has to occur. Therefore, A union B is said to be a certain event. Okay. Oh, here we go. It's time for the complement rules. So we remember that very well. The probability of a complement equals 1 minus the probability of A, which you recall from earlier was 0.25. And that gives us a final result of 0.75. Okay. What about B complement? Well, we'll use the same rule, of course. And you'll recall that the probability of B was 0.75. So therefore, we end up with 1 minus 0.75, which is 0.25. All right, now we save the best for last. We've got two conditional probabilities. And these are done in exactly the same way as all the other ones we've ever done. The first thing to do is write out the definition, which is the probability of A and B, and then we divide that by the probability of B. But remember, the probability of A intersect B is 0. So this one is equal to 0, no matter what's in the denominator. And comparably, the same thing must be true for the probability of B given A, because we have the probability of the intersection divided by the probability of A, and therefore we have 0 over 0.25, which is 0. Okay. All right. Now we have some conceptual questions. Are A and B mutually exclusive events, and why or why not? So remember, don't forget to answer that question. Don't just say yes or no. And here we have some options. Well, first of all, the answer is yes. And why is that? Well, there's three potential reasons for it. A and B have no elements in common. All right, so let's go back. Let me just grab these so you can see that visually. There we go. So you can see just by looking up there, they have no elements in common, or the intersection is the empty set, or their probability is 0. The probability of A and B is 0. Any one of those is enough to prove that A and B are mutually exclusive. And for the independence, remember we saw earlier that independence requires two different things to be true. Here we are. If either of these is false or both, then that's it. Okay, so we're going to ask ourselves first, is the first condition true? And you might recall that just from a few minutes ago, we discovered that this probability is equal to 0. And before that, we discovered that the probability of A is 0.25. Well, are they equal to each other? No, obviously not. So that being the case, it must be true that A and B are not independent of each other. All right, very good. Now we're ready for another joint probability table. Except this time, instead of coffees, we're looking at sodas. So what's different this time? Look at this. We've got flavors of soda and regular or diet. Coke, Dr. Pepper, and Sprite, all of them organized according to whether they're regular or diet. So the probabilities that we'll be calculating are the same as we did on the previous problem set, but of course the numbers are different. So we start with the joint probabilities like CNR, regular Coke, 0.32. Okay, easy enough. How about P and D, Dr. Pepper and Diet, Diet Dr. Pepper? And then SNR, regular Sprite, right here at the intersection of regular and Sprite, 0.15. Now, how about S? S in this case means Sprite. And so we look for the column total of 0.26, and that's all we need because that includes both regular Sprite and diet Sprite. All right, now how about R, regular? 0.61 is the regular soda in this sample, and of course 39% is diet. So the probability of R is 0.61. Oh, here we go. We have some complement rules. First, I have to split the screen. So the first one, the complement of R complement is the probability, of course, is 1 minus the probability of R, which up here you can see is 0.61. And that gives us a final result of 0.39. How about, okay, that was the only one. All right, then C or P, these are the ones where we're taking advantage of the simplified addition rule. So C or P means Coke or Dr. Pepper. And because they're mutually exclusive, we can simply add up 0.48 with 0.26 to come up with our solution of 0.74. Now we can do the same thing with Dr. Pepper and Sprite. We can simply combine these two columns, and just by coincidence they're equal to each other, so the sum is 0.52. Nice. Now, here's the conditional probabilities. R given C. If I choose Coke, what's the probability that it's regular Coke? So in the numerator, we have the probability of R and C, or regular Coke, over the probability of just Coke, which is 0.48. And that means 2/3 or 0.667. All right, so far so good. All right. How about D given S? So the pattern is always, oh, what happened here? We got a little squished together. We have D and S in the numerator. That's diet Sprite, 0.11. In the denominator, we have just plain Sprite, which is 0.26. So that ratio gives us approximately 0.423. And then there's one more here, P given D, which means Dr. Pepper given diet. So in the denominator, or in the numerator rather, we have P and D, diet Dr. Pepper, which is 0.12. And then in the denominator, we have D for diet, 0.39. And so that ratio is approximately 0.308. All right, so that question is done. Now here in this one, we have something extra at the end. We have some questions about combinatorics. Okay, remember way back in the beginning of this chapter 11, we were introduced to factorial, arrangements, permutations, and combinations. The formulas are not terribly difficult, but we have to know which one we're supposed to do. That's obviously a huge deal. So let's get to those. Hopefully we'll see if we did not forget any of these ideas. An author has written 8 books and wants to display them on a shelf in his office. How many different arrangements are possible? So if you recall, the number of ways of arranging n objects is n factorial. So here, all we have to do is take 8 factorial, and that's equal to 40,320. Now, on your calculator, you do have this function. Where is it? It's hiding. It's in the very bottom left-hand corner. And it's very simple and easy to use because all you have to do is write 8 factorial and you're done. It's so simple. You don't even need the equal sign. Okay. Now, part B, in a game of 3-card poker, how many different hands are possible using a standard deck of 52 cards? Now, what this implies is that we have a deck of 52 cards and we're all getting 3 cards. We're not arranging the cards. We're choosing a collection or a smaller set from the entire deck. The order in which we are dealt the cards has no relevance to the value of the hands. So therefore, each hand is considered to be a combination. And with that in mind, we can now figure out how many combinations we can create when choosing 3 cards out of 52. So you might recall the formula for combinations is over here. NCR equals n factorial over n minus r factorial times r factorial, where 52 in this case is n, r is 3 because we're picking 3 cards from a deck of 52. Now you can plug these numbers in over here on the right, but with your calculator, you probably should do this. 52 factorial, actually, let me write this a little differently. I just realized, yeah, I think I'd like to fix this up a little bit. It should technically be 52 x factorial divided by 49 x factorial times 3 x factorial, close parentheses, and equal. That should get you where you're going. Okay, so that little button, x factorial, will give you 52, which is an enormous number. I've got it up here. And don't forget that little e there in the window means scientific notation. So don't be shocked when you see this because it's such a big number. There's no way they can fit it all on the screen, and they give it to you in scientific notation. They're all big. 52 factorial, 49, not 3, but the other 2. So don't be shocked when you see this. But as long as you follow these steps, you will get the right answer, which turns out to be 22,100. Yeah, that's true. It's kind of a lively little operator, isn't it? Yes, that's a good point. I like that. It's very upbeat. It's saying, yes, 52 factorial, yes. 49 factorial, yes. What a time to be alive, yes. That's what it feels like. Yes, I agree. So I'm double checking mine real fast to make sure those keystrokes are indeed the ones that will give you your answer. Yeah, it works out just fine. All right. And then there's one more. We have a class of 10 students. The loudest kind of math, that's right. Most of it is very serious, but factorial is exuberant. Okay, it's enjoying itself. How do you like that? But anyway, we have 10 students in the class playing an investment game. Ooh, maybe we should have done this, in which there's a prize of $100 for finishing first, $50 for finishing second, and $25 for finishing third. In how many ways can the prizes be distributed in this class? Now here, these are clearly permutations that we're looking at because the order of selection matters. For example, the selection 214 means that student number 2 wins $100, student number 1 wins 250 rather, and student number 4 gets 25. That's a very different outcome than, let's say, 421, even though they're the same numbers, because this means student number 4 gets the $100, student number 2 gets the $50, and student number 1 gets the 25. Okay, so now the formula, as you might recall, is right here. And it's NPR equals n factorial over n minus r factorial. Here, n is 10 because there's 10 students in the class. R is 3 because there's 3 prizes. So when you plug those in, or here algebraically, you've got 10 factorial over 7 factorial, which is what you're doing down here with your calculator. And either way, the final result is 720. So that's it. So now we're in pretty good shape with chapter 11. I think you'll agree. Nice. This will certainly cut down on your studying time for the final exam. All right. Now, chapter 12, as I said before, is our introduction to statistics. We started to learn about some very important concepts. Let me just quickly review them with you. And then, where did it go? Oh, here we are. We have a video that helps, hopefully ties a lot of this together. So remember, we define a population and a sample. A sample is a subset of the population that we're studying. And then, where are we? We introduce our measures of central tendency, of which there are 3 that we want to know in this class. Mean, median, and mode. We actually spent a fair amount of time with these first 2. So the sample mean is used with the following formula, but as complicated as it looks, all it means is take all the elements in your sample, add them up, and divide by the sample size. We introduced the summation operator, of course, because we need that to get our results. And so we had a case with 5 sample elements, and we calculated the sample mean very quickly and easily as, there it is, 2, because when we add up the elements in the numerator, we got a 10, and then we divided by the 5 elements, and then we ended up with 2 as our sample mean. Then we noted that there's a separate formula for the population mean, where the only difference is that we refer to the mean as mu, the population mean, and we change the lowercase n's to uppercase n's to indicate that this is the size of a population. But they're both the same thing. You can tell in both cases, we're just simply adding up all the elements and dividing by the number that we have. All right, let's see. We also introduced the weighted average. If you recall, this is used in cases where we have many repeated elements in our sample, or if each element is not equally important in some way, like grades, okay? Every class is different because of the number of credit hours. So we saw 2 examples of this. And also, by the way, we noted that there's a separate formula, as always, for both populations and samples. In this case, they're the same formula with slightly different notation. The process is exactly the same. And we also know the weights are basically frequencies. How often does this element occur in my sample? That's really what the weights are capturing. And we saw this lottery example where we had a single prize of $1,000, 10 prizes of $500 each, and finally 100 prizes of $10. And we wanted to know the average prize received by a lottery winner. Now we know that we should not just add up those 3 prizes and divide by 3 because they did not all occur with the equal frequencies. So instead we used our weighted average or weighted mean formula. And we made sure that we noted here, though, that the weights are the frequencies of the prizes. The X's are the actual prizes themselves. If you get this backwards, by the way, you can't get the right answer. So remember, the weights are basically frequencies. And then when we did our calculations, we discovered that the mean is 6,306. And so, of course, it's much closer to the $100 prize, or rather $10 prize, than the 1,000, because there's so many $10 prizes. We also did a similar example with the weights. Well, we did a weighted average with your GPA. And the reason why this is necessary, of course, is because each class might have a different number of credits. So the weights are higher in this example for pre-calculus and physics than they are for English and history. If we just added up these 4 numbers and divide by 4, we're not going to get the right answer. The weights are different. These credits are weights. And since they're different, we must use a weighted average to come up with this result. And so we did all that work, and we discovered that the weighted average was 3.29. Not bad, huh? 329. That sounds pretty good. All right, now, what else do we cover? The median. We introduced the median by explaining that the median is simply a number that divides our sample or population in half. Half the elements are below and half are above. It's a different idea than the mean. And we also discussed at some point when you might use the median versus the mean. So how do we calculate a median? Oh, and of course, we saw a couple of simple examples. Like if we were told that the median age of all Americans is 28, that means that half the population is under 28 and half are above. That's all that it means. It doesn't guarantee that the mean is 28, although it could be. We had another example of scores on an exam. Suppose you were told that the median is 82. That just simply means that half the class got a score under 82 and half were above 82. That's pretty high for a median, I think. I mean, 82, that is usually, I don't know, it depends on the class. So we calculated a sample median with this set of elements that we've been using all along. And the first thing we always do in these cases is sort the data from low to high. And so when we do that here, we've got -1, 1, 2, 3, and 5. And our goal is to find the middle of the data, which is easy with an odd number of values because all we need to do is go right to the center. So for this case, the median turned out to be 2. The tricky part comes when there's an even number of values in our sample or population. Like here, we have 6 observations. What do we do now? Well, we do the same thing we've always done. We sort the data from low to high. The difference now is that we're going to average out the 2 observations in the center. Okay, so if I sort them out like I did here, it turns out that my median is halfway between 2 and 3, which is 2.5. And it works because half my elements are below that point and half are above. Okay, now there's no formula for the median. Instead, it's a procedure which basically consists of 2 steps: sort the data and find the value in the middle. The population and the sample median are calculated in exactly the same way. Now, we also discussed when you might prefer to use the median to the mean, and that was in the event that we had outliers in our data. So remember, outliers are extremely large or small values. And so we'll skip ahead and look at this example we had here, where we've got 6 elements, but one of them is clearly way above the others. So 100 is substantially larger than the others. It is therefore considered to be an outlier. That's a problem, because if we calculate the mean, we're going to get a number which is not really representative of the center of our data. For example, if you look at this, you'll see that the average of these 6 elements is 19, which is not very meaningful because most of the observations are below 19 and one of them is well above 19. So the mean doesn't have such an big importance when we have an outlier like this. But on the other hand, let's look at our median. By sorting them out from low to high, we end up with this result. And so we're averaging out the 2 in the middle, which just so happen to both be 3s. So our median turns out to be 3. And I think you'll agree that 3 is a much more meaningful measure of the center than 19. Okay. So this is when we, so notice this is why we want to use the median when we have outliers and not the mean. The rest of the time, when there's no outliers, we typically use the mean because it's more intuitively clear to people what it means, and also it has more convenient mathematical properties than the median. So we usually reserve the median for cases when we have outliers. Now, then I don't think we went over this last time, did we, the mode? I think we may have stopped right here last time. All right. Did we do this?
No, I don't think so.
Okay, good. So we'll start. So this is the first new material we'll be doing today then. All right. Now the mode won't take that long to go over. The mode is the easiest, but maybe the least useful of all the measures of central tendency. It is defined as simply the most frequently observed observation in a sample or a population. So it's very different from the mean and the median. It's just the most commonly observed element or frequently observed element in our sample or our population. All right, let's take a look at this sample. Now, just like with the median, we're going to sort everything from low to high. And when we do, we end up with this. Now, if you notice, there's only one value that's repeated. That's the 3. And therefore, 3 becomes the mode of this sample. And you can see it's really, really simple. Now, there's some quirky things about this mode. It turns out that we could actually have no mode at all. And we can also have more than one mode, which is something you do not see with the mean or the median. Okay, so The mode does not have to be unique, and it does not have to exist. Let's look at some examples. Look at this one. The data have been sorted already. What's the mode? Well, there isn't one because none of the values are repeated. Well, that's awkward. You don't run into that with the mean and the median. There's always a mean and there's always a median. Here, that isn't the case. So it's not a terribly useful measure when we don't have any repeated values. Now, here's another case where you'll see the opposite. What do I mean by that?
You mean that there's going to be multiple repeated numbers like that are repeated same amount?
Exactly. So let's take a look. Now, what do you notice about this sample? There's both 2 2s and 2 7s. So they're basically tied for the most frequently observed values. And so we say in this case that there's 2 modes, 2 and 7. So our sample has 2 modes. And again, you're not going to see that with the mean and the median. 2 modes. Well, that makes things a little bit more awkward. Now, there's terminology we can use for these to describe these cases. There's always terminology. All right, let's see what these are. How about this one? A sample with a single mode is said to be unimodal. Or, of course, you know that the prefix uni means one. A sample with 2 modes is said to be bimodal because we know that bi means 2. And of course, you can carry this on as far as you want. If you have
Bimodal, polymodal. Yeah.
yes, exactly. 3 would be trimodal, and then it goes on and on and on after that. So you can have as many modes as you want. I mean, anything is possible with modes. Well, that also makes things a little bit more awkward. Now, and I do want to point out here that just like with the median, the calculations are identical for both the sample and population mode. And in addition, there's no formula. Instead, it's simply a process. I might as well add this last part. The process comes in 2 steps. 1, sort the data. 2, find the most frequent observations. That's all there is to it. So there's no formula. It's a process. Okay. Now, you might wonder then, when might this mode come in handy? Here's an example. Suppose that Apple has decided that the next iPhone will only come out in one color. They must therefore find the most popular color. How can they do that? Well, they can do surveys. Imagine themselves insisting that everybody who comes in the store must tell them what their favorite iPhone color is. Otherwise, they don't get in the door. They could do that. They would never do that, but let's say they do. And so they start gathering up the results. And so let's say here's the first group of people, and these are their responses. And you can see by a slight margin, more people said black than anything else. So we would say in this case that the mode of this sample is black because there's more blacks than silvers or blues or coppers or reds or silvers. So the mode is black. Now you're not going to see, here's the nice thing about this. You cannot apply the the mean and the median to non-numerical data like you can here. But you can apply the mode to it. So if you're looking to, let's say, colors or flavors or whatever the case may be, you have to use the mode because the mean and the median would be undefined. Undefined. Okay, there's no such thing as a median or mean of non-numerical data. So this is where the mode can be very useful. So that's why it's often used in disciplines like marketing. Marketing, of course, is all about figuring out what people want and then giving it to them. So when Apple tries to decide, what color should we manufacture? Well, they'd better find out from their public what colors people actually want instead of just randomly choosing them. Like suppose Apple said, nah, we know what we're doing. Let's just make them all yellow. And then they discover that they've lost half their sales. Then they wonder why. No, they have to decide this based on research into what people actually want. And so the mode can be very helpful in a case like that. Okay, now what's coming up next is a little bit involved. It involves comparing for each sample the mean, the median, and the mode, and that will provide us some important information about our data. But now, by the way, this is about where I left off with my 8:30 class. So because this is a fairly complicated topic we're about to dive into, I think our best bet would be to stop right here and not try to start something that's complicated on a Thursday morning. So we'll cut it off here. We'll pick it up at this point next Monday, and then we'll just carry on from there. How does that sound? In the meantime, I'll post the solutions to the problem sets. So you can go over them over the weekend if you want to, and see if you got them all right, or if you didn't, see if you can figure out why not. And then in the meantime, I'll just see you all then on Monday.
I have a question real
Yes,
quick.
go ahead.
Which email were we supposed to send the midterm to again? I just want to make sure I sent it to the right one.
Oh, you know what? It doesn't really matter. I was hoping you'd send it to the purchase account, but unfortunately the purchase account has very limited space, and
I
some
see.
might not have been able to send it over there. So if you send it to my Dr. AA account, that's fine too.
Okay.
That's not a problem.
All right,
And
great.
by-
Thank
and
you.
By the way, I'm going to be spending this weekend up to my eyeballs in exams. Whatever exams I owe you, they'll be done this weekend. Okay.
Okay, cool.
Worried about it. So yes, don't worry. I'll be chaining myself to my desk here and correcting
All
you
right.
all weekend. Okay.
All right. Sounds
All right.
good. Thank you.
Okay. So I'll see you all next Monday.
Thank
Oh,
you.
yes.
All right. Take care.
Okay. Bye.
Can I
Thank
talk-
you.
could I-
Bye. Britt, did you want to ask something?
Yeah, could I talk to you like after class? Cause like.
All right. We'll hang on here for a minute. Oh. We have a lot of people who do not want to go home.
I guess they like math so much.
I
that they
know. I'm impressed. Is it super confidential?
No, not really. So first of all, I'm really sorry about being late. How will it affect my grade?
In no way.
No way. Okay, thank God. Number two, you received my math midterm, right? I turned it in on Sunday.
I'll double check. Yeah, I've got them all sitting there. I'll double check. If I can't find it, I'll just let you know, and you can send me another copy of it.
Okay, that's fine. Thank you.
Okay, you're welcome. Anyone else? All right, see you next time. Bye.